Hello everybody. In this video, we are going to do a quick little lecture on confidence intervals and what exactly do confidence intervals mean. So remember that when we are talking about like our population statistics and samples, let's start off with just what our population is. So our population is our big group of interests that we want to make some conclusion about. And a lot of times we are interested in the true mean of a population, and we write that as mu. But the problem is that we don't know what mu is. We have no idea what this value is. So what we do is we then say, it's like, okay, I need to know something about my population, but it's probably impractical for me to talk to everybody in that population. So I'm going to have to take a subset. I'm going to have to do good sampling so my subset actually represents my population. And I'll call this just my sample. All right, so I've got my sample. And from my sample, I can get a sample mean called X bar. Now, I know that this sample isn't a perfect representation of our population. So we could say, let's suppose we have this big number line. And let's suppose that our mean that we found, our X bar, was equal to 50. And we'll say that it might go all the way up to something like 70 and all the way down to, I don't know, something like 30. All right, so we got a decent amount of standard deviation going on. So as we do this, what we know that it's like, well, if I were to take another sample, let's say, if I was, whatever, we'll just keep going with how we're going. If I did another X bar, I might get something a little bit lower, something like 46. We'll say that this next sample I got was a sample of 46. And then the next time I got something that was equal to like 60. And I got another X bar. And so if I do this over and over and over again, what I can do is I can start building this histogram of X bars, and I can get more and more. And as I do this, I start realizing that, hey, my X bars are getting centered kind of about a certain value. Now check this out. Notice how I kept drawing this, and what does it look like that I'm drawing? I'm drawing basically a normal distribution, and this is kind of central to what's called the central limit theorem. Let me put this up. And it follows these like one or two things. So it says that like X bar, so like the distribution of, we'll say, the distribution of X bar will be approximately normal if one of the two things are true. If our sample size is like greater than or equal to 30, or if the original distribution is normal. Okay, this gives us a ton of firepower of what we are able to do at this point. Because we can basically say, hey, if I know that the original distribution is approximately normal, where like most of our results are kind of centered about the middle, where they kind of die off as they go above and below what the middle is, that's kind of normally distributed. Or if the original distribution is crazy weird, the X bars are going to be approximately normal. All right, we're not going to go into a deep dive into the central limit theorem, but basically we're going to leverage the fact that if the original distribution is normal, or if the sample size is greater than 30, X bars are going to be approximately normally distributed like we saw here. So now it's kind of unrealistic if we were to go through and suggest that we should do like hundreds and hundreds and hundreds of samples, build the distribution, and figure out what this sample mean actually is. Now, you could do that, and it would give you some pretty good results, but a lot of times we just get a single mean. So what can we do from there? Well, we can leverage the fact that we know that the central limit theorem is going to happen. And what we can say is that, okay, I want to be pretty confident. So let's write that over here. I want to be confident. I want to be confident um, that like I can capture capture the true mean with a range. And what we're going to be building is like a confidence interval, which basically says that, hey, I'm going to calculate out my sample mean here. And I'm going to go above and below this mean to get a interval of where I think that the true mean is. Because like, I know that like, if I were to get another sample, it might be down here, or another sample, it might be up here. And I think that the true mean is going to be roughly between these 2 points. With what confidence? Well, when we say that we want to have something with like 90% confidence, or like we'll do like 95% confidence, it means that we're taking this normal distribution and we're basically saying, okay, I can just shade between those 2 points, and that's basically 95% of the area under the curve. And so if I give you this lower point and this upper point, I'm like 95% confident that this range has captured the true mean. I could become more confident or less confident. Let's say that I want to be 90% confident. Well, if I want to be 90% confident, I would be a little bit narrower on this, right? I'm able to have a narrower confidence interval, which is handy. It gives me a narrower range of where I think that the true mean is, but I'm less confident. Look, there's all of this space over here where the true mean could have landed. Okay, so if that's the case, then like, what is the bit? Maybe I don't want to I want to be 100% confident. The problem with 100% confident is that a normal distribution extends in both directions to negative infinity and positive infinity. So if we were 100% confident, our range would be completely useless. Most of the time we have somewhere between like a 90 to 99% confidence. And we can use the definitions of a normal distribution to figure out how far above and below that should be. Okay, so let's get ourselves a little bit of a equation to help us out. To say, okay, how do we actually calculate out this confidence interval? Excuse me for a second as I erase. Okay, so here's our confidence interval. So our confidence interval is going to be like this. So we take x bar and we go plus or minus, and we go plus or minus what's called the margin of error. All right, so the margin of error is this distance from the mean to the lower end and the distance of the mean to the upper end. So the confidence interval it's symmetrical because the normal distribution is symmetrical. So we've got plus or minus this margin of error. So we've labeled that right here, margin of error. Cool. Okay. How do we calculate out the margin of error? Well, margin of error is equal to a t critical, we'll get to that in just a little bit, multiplied by our standard error. Standard error kind of sounds like standard deviation, and it's close. It's an adjustment of the standard deviation. So the standard error is equal to our sample standard deviation divided by the square root of our sample size. So we call this, again, the standard error. This is how we calculate it. And we get our t critical. It's like, okay, so I can calculate this. I have my raw data, like, 10, 20, 21, 33. I can calculate a standard deviation there, or my sample standard deviation. So I'll just say that that is like S. I can calculate out my sample size. That'd be something like the number 4. I can calculate my X bar here. But how do I get this t critical? All right, so the t critical, let's kind of go over here, has to be calculated from either Excel or it has to be calculated from a program. Essentially, what this t critical tells you is how many standard deviations, or how many standard errors away from the mean is this critical point. Okay, so how do we talk about this? Well, let's talk about our distribution here. So a normal distribution, how we draw it, if you notice, we have like concave up right here, we have concave down right here, and we have our graph goes concave up again. Again, this is not the most perfectly drawn graph. If you remember from geometry, our inflection point right here is where a distribution switches from, for the normal distribution, switches from concave up to concave down. And it happens again on the other side at the same distance. My graph is not perfectly drawn. This distance right here, that distance is known as our standard error. Cool. Okay, so there are definitions in our t-critical for how many standard errors do we need to go to capture a specific percentage. So in order to do this, you have to do it. There's no way to like just calculate this without some really intense mathematical approaches. But we have tools that we can just ask what is the t-critical for a given confidence level. So if we know that the confidence level is equal to 95%, that's really important. We also know that alpha is going to be 5%. All alpha is just 1 minus the confidence level. Okay, how does the confidence level plan? Let's go back up here. So if we have, let's say that this is our 95% confidence interval. Let's kind of erase this out. Let's go back to just 95. Say this is a 95% confidence interval. And we'll say that our lower bound is something here at like 40, and our upper bound is at 60, and that is our confidence interval. If that's true, we're 95% confident that the true mean is kind of located in this range between 40 and 60. But 2.5% of the time, and 2.5% of our distribution is above and below that. So it means that alpha basically tells us what percent of the time is our confidence interval. Like if we make these confidence intervals over and over again, are we going to miss the true population mean? We want to capture it most of the time. And if we follow the right processes, we will capture it 95% of the time. But just from randomness, does it happen sometimes that we just get a weird sample that doesn't really match up with how the population acts? And that is absolutely true. So we know what this confidence level is, and based upon our confidence level and our alphas, we can know where this critical point is, and we can then get our t-critical, and then we can plug it in and calculate out our confidence intervals. Okay, so that's enough of kind of like just a little lecture, and we will go and do a video of how do we actually calculate these values so we can calculate a confidence interval based if we are given sample statistics from somebody who's already calculated like the mean and the standard deviation, and how we can also do it from just gathering raw data. Anyways, hope that kind of helps describe our confidence interval.